What is the angle that maximizes the range of a projectile? How are the projectile motion equations used to calculate a projectile's range? These are the questions that we will explore in Investigation 6B, Projectile Motion. Tossing a ball, shooting a basketball, we all have experience with projectiles and trying to predict where they will go. Projectile motion occurs whenever a moving object is under no force except gravity. The equations of motion for each coordinate axis are independent of each other, so we can analyze them separately. We combine the equations for the two independent directions, x and y, to predict the range of a projectile. Your students will first try using various angles to see how far the projectile travels and launch the projectile as far as possible. Next, they will use what they have learned about predicting projectile motion to land their projectile in a cup. For this investigation, each student group will need a mini launcher with its stand, a C-clamp, a projectile, a push rod, a measuring tape, and a cup. Heavy cardstock or carbon paper and plain white paper is useful for recording where the projectile lands. Safety glasses are also recommended for each student not already wearing eye protection. Students should assemble their equipment as you see here so that their projectile will land on the lab table. The C-clamp, which you can't see because it's behind the bracket, fastens the launcher to the table. The angle of the launcher can be adjusted as needed. To help me identify where the projectile lands, I've taped paper to the table and covered it with carbon paper. When the projectile hits the carbon paper, it will leave a small mark on the paper that I can use to measure the projectile range. You might also find it useful to tape a measuring tape to the table. In Part 1, students are challenged to figure out what angle will give the longest range for a projectile. Each group will launch their projectile at various angles, measuring the distance traveled for each angle. Instructions for this lab are to use 2 clicks to launch the projectile, but since our studio is small, we will use 1 click so that the projectile will land on the table. You may need to make similar adjustments for your lab space. For each trial, students should set up the launcher using the angle indicator to measure the angle. They should press in the ball using the push rod and pull up on the string to launch it. These labeled dots are from previous launch angles of 20 to 55 degrees. This dot is the last launch at 60 degrees. Starting from the launch position on the mini launcher, students will measure the range of the projectile, and that's where the measuring tape comes in. And they'll record their launch angle and the range for table 1 for each angle. In this case, to the nearest centimeter, I have 1.10 for 60 degrees. As this data shows, students should try launching the ball at many different angles, including 30 and 60 degrees. It is important that students use the same initial speed for each launch by pressing in the same number of clicks each time. Your students can use their data from Table 1 to answer the questions for Part 1. In Part 2, students try to figure out where to place a cup so that it catches a projectile launched at 60 degrees with a different speed, a different number of clicks than in Part 1. To make it challenging, students must calculate the initial speed of the projectile using the projectile motion equations, and then use that value to calculate the projectile's new range using the range equation. First, students will launch a ball horizontally across the room and onto the floor. and then measure the range of the projectile and the height of the launcher above the floor. Using these values with the equations of motion in the x and the y direction, students calculate the ball's initial speed. And then they will calculate the expected range at 60 degrees. The teacher key and the lesson PowerPoint both demonstrate these calculations. After the calculations comes the fun part. Can we get the ball in the cup? Not by trial and error, but by simply placing it at our calculated range. Make sure that the launcher is set to 60 degrees. Since I'm trying to catch the ball, not knock over the cup, I cut my cup down to about 2 inches high and taped it to the table. Some clay can soften the hit and keep the ball from bouncing out of the cup. Students can use their experience to answer the questions in Part 2. Applying new knowledge gives your students a chance to use what they have learned in answering a few questions. Answers are given with numbers and graphs in the teacher's key.